We're, of course, celebrating tonight Earth science in general, which really exemplifies the idea that everything that NASA leads really to the ultimate goal of protecting and improving life on Earth. So I want to quickly talk about kind of the view of Earth, and I'm going to talk about a kind of zoom in, zoom out, right? Because for us to understand the Earth, we must see it in the broader context. And of course, closest to the Earth are terrestrial planets in our environment, and each one of those planets tells a story of how a planet can end up with a different destiny. When we study those planets, we learn about the processes that shape the Earth, about our past, and about our future. Very similar to the Earth, for example, is Mars, that started together with the Earth, but looks very, very different. We know now that Mars, of course, was very wet, and it lost a lot of the water, and we know now from actually one of the Goddard-built spacecraft that a lot of the reasons it lost that water is because of the scavenging from the solar wind, kind of ripping off over millions of years water out of the atmosphere. On the surface of Mars, of course, we landed with Curiosity rover near Gale Crater, and we really went into kind of a beach environment with rivers and what used to be lake beds and so forth. And we're learning about this and the amazing landscapes there, and really thinking about what could be in the future here of an Earth where the sun gets hotter and hotter, for example, as we go in kind of astronomical timescales, so forth, going forward. When we look at the outside of the solar system, and you already mentioned Cassini, we're looking at this amazing planet, Saturn, and its rings, one of the most majestic planets, just absolutely amazing when you see them, and even a telescope. I remember as a kid looking at it, it's like, there it is, the rings, it's amazing. Well, what's even more stunning is that there's moons out there, Titan and Enceladus, that we're now really thinking about in the context of the Earth, because of the fact that they have oceans and they spurt out organics in the case of Enceladus, something that gives us an entirely new perspective as to where we should look for life and how, in fact, we should do that. You can zoom back even more, and what you look at is a galaxy, and you remember that in that galaxy are billions and hundreds of billions of stars. Well, how many of them are like the Earth? I remember when I did my PhD in '96, we thought, well, perhaps there's planets. 96 is 1 year after 95, for those of us geeks, like you said. 95 is the time the first extrasolar planet was announced. So we thought, well, perhaps 10% of these stars may or may not have planets, perhaps even less. Well, oh no, there's many, many more of those now. And this next thing is just one example that we actually discovered with Spitzer, where we basically have a small star with 7 planets going around it. This is Spitzer following up on a ground-based observation. 3 of those, we think, are in the habitable zone, based on just the distance and temperature of the host star. We now know, based on Kepler and other observations, that it's very common to have planets. Every average star will have a planet. Many of them will have Earth-like planets. So it's an abundance of Earth like us, potential Earth like us here, but we have one home, and that home was recently visited by a spacecraft also let out of Goddard, OSIRIS-REx. It's actually on the way to a little body out there that it's going to collect matter with Bennu and bringing it back. But when it flew by the Earth, it took this picture, and it reminded us that, like coming from this deep space, coming to the Earth, how beautiful our planet really is, but also how fragile that planet is as we're living on it. It reminds us all these stories. I think many of us were in Australia when it flew over it. Some of us were in California, there at the top of the picture. And that's really kind of zooming back in, and the talks will be zooming into our beautiful planet that is such an important planet and subject, very worthy of our study and full attention. So with that, I want to introduce Marshall Shepard, our next speaker. And of course, Dr. Marshall Shepard is a leading international expert in weather and climate. and is the Georgia athlete. You like that picture, right? The Georgia Athletic Association, a distinguished professor. That means, in kind of in academic speak, the best of the best type of professor at the University of Georgia. And you're also an associate department head, of course. You were the 2013 president of the American Meteorological Society, the nation's largest and oldest professional science society in atmospheric and related sciences. And prior to the University of Georgia, Dr. Shepard spent 12 years as a researcher at NASA Goddard. He was the deputy project scientist of GPM. It's actually that mission that helped make predictions for the very storms that were going over the house of my father-in-law. And you know, so for me, this is really personal when I look at these missions now, of course, them being in our portfolio, but them affecting our lives in a direct fashion. He's safe, in part because of these predictions that are that came from that mission that you were directly working with, Marshall. I also want to say that, of course, Dr. Shepard received his BS, MS, and PhD in meteorology at Florida State University, and he was the first African American to receive a PhD from Florida State University Department of Meteorology, one of the nation's oldest and most respected. I'm just excited to welcome you, Marshall.
Thank you and good evening. Now go far enough into space and Earth looks like any other star or planet in our night sky. But of course, we know it's not. Come closer and we see a planet bursting with color. It's bursting with life. It's covered by just the right amount of ocean, just the right amount of forested continents. It's protected by a dynamic yet thin atmosphere that roils with weather and storms. Now, we understand the cosmic odds that allow us to carve out our lives here on Earth. Yet there is so much more to learn about our home planet. The world gets more populated, more complicated every day. How are we going to improve life on Earth? How are we going to safeguard this planet? Who is going to lead the continuing discovery on Earth? As Thomas showed us, NASA's exploration of our solar system and deep space is taking us closer than ever to planets than before. But that view from space is also vital to understanding the most complex planet we know, Earth. To take on Earth's challenges, we need not only the vantage point of space, but we also need the technology, grit, and quest for discovery that we use to explore the universe as only NASA can. Now, it's important to note here that Earth science has been at the core of NASA's mission since the beginning. Let's take a look at the Space Act that created NASA. It talks about for the benefit of all mankind. It talks about advanced knowledge of Earth's atmosphere, the preservation of the role of the United States as a leader. Now tonight, I'm going to talk about things from a hurricane perspective. We want to share with you a few stories of how NASA is leading the planetary exploration of Earth and continuing to provide return on investment to every U.S. citizen. In particular, we want to take a look inside the complex world of water. Sometimes there's too much, sometimes there's not enough. So let's pivot now to talk about the hurricane season of 2017. And by the way, as we speak, there's a hurricane possibly developing down in the Caribbean that will affect the Gulf of Mexico and Gulf states later this weekend. Now, 2017 has been an extraordinary season. Hurricane Harvey was the first major hurricane to make landfall in the U.S. in over 12 years. The iPhone and Twitter weren't around then. It was also the most significant rainfall event in U.S. history. Hurricane Irma remained a Category 5 hurricane longer than any storm on record in the Atlantic. And of course, Hurricane Maria, rapid intensification, power, humanitarian crisis. Now, look, I'm a meteorologist, And if you follow me on social media or read some of the contributions I write for Forbes, many of us knew that these storms were going to do what they did. And that's really tough as someone that has knowledge to see that happening. But there is, I guess, a bright side, because we know that science has allowed us to advance knowledge, predict these storms, and possibly save lives. Now, this hurricane season, I want to highlight two stories. One, with each of the three major storms that I've talked about, we can see, even in that glimmer of despair, a success story, where the view from space has improved our ability to forecast or respond to hurricanes. And the second storyline is that we saw three major storms that highlighted absolutely fundamental questions that NASA is trying to answer about hurricanes and how they work. And I'll get to those critical questions in a moment. But first, let me acknowledge our partners. NASA is a research and development agency pushing the envelope on technology, new knowledge generation. We work very closely with our partners at NOAA, the USGS, other federal agencies, and in collaboration with many of our industry partners that are here in the room tonight. That partnership and collaboration is critical to everything that you're going to see tonight. And so we thank everyone that's represented here from those various entities. GOES 16 will soon move to become GOES East in its operational orbit parking. GOES S launches next spring, and JPSS-1, our polar orbiting satellite system, launches next month. They're all a result of partnerships between NASA, NOAA, and industry. Now let's talk about some of those success stories that I mentioned earlier. Hurricane Harvey's rainfall. Now, as a meteorologist, when I was looking at the forecast models and I saw them saying 3 to 5 feet of rain, I couldn't believe it. I literally couldn't believe it, but they were right. Days out, they were right. This is a testament to decades of advancement. This information from these satellites, from advanced models, are saving lives. Let's take a look at Hurricane Irma's track forecast. This is 5 days before Hurricane Irma made landfall. Watch the lines. The forecasts were spot on 5 days out. Now, yes, there was a little wiggling back and forth as it neared Florida, but where we are in meteorology, this was an amazing forecast. And science got us there. Now, some ways that you might not think of, and you heard Chris mention this earlier, Puerto Rico, Maria knocked out power all across that island. What you're looking at here is a brand new NASA capability that gave first responders block by block detail of where power went out. It is produced by scientists at NASA Goddard and NASA Marshall. It combines nighttime data from the Sumi NPP satellite with 4 other types of satellite data. And the result is a high-definition view of night lights before and after Maria. Look at the streets and city blocks that you can see. But here's what's more important to citizens, particularly our citizens in Puerto Rico. This map you're looking at was put directly in the hands of FEMA and the National Guard last week, directly in their hands, so that they can map out a response strategy. The first time this satellite data product has been provided to first responders. Now let me pivot back to those research questions. The science is helping us understand them, and there's still many challenges ahead, but NASA's there, and our partners are there. Let's go back to Harvey's rainfall. The volume of rain raises questions. Are severe storms more likely to produce more rainfall in the future? NASA is in a better position to help figure that question out. In 2014, NASA, in partnership with the Japanese space agency JAXA, launched the Global Precipitation Measurement Core Observatory, GPM. Now, this is the most advanced orbiting rainfall measurement system ever conceived. NASA is coordinating and fine-tuning rainfall measurements like never before. The core satellite has a radar and passive microwave imager that helps calibrate a constellation of satellites, 10 of them, to produce unprecedented global rainfall around the world. That's weather, folks, that you're seeing manifested in rainfall. And at that scale that GPM can provide, not only does it provide science, we can help with landslides, flooding, and other things that affect society. That's U.S. leadership. Now, we've heard questions about whether extreme rainfall events are going to increase, the physics of a warmer atmosphere leading to more moisture in the atmosphere, more big rain events. In other words, what's the weather going to be like in the 21st century going forward? These are questions of the day that scientists will address, and GPM will be there to help. But rainfall from Harvey was not the only hallmark of this season. Let's go back and take another look at the Irma track. And what you'll see, look at those warm ocean waters that Irma had to tap into. But look inside the little hurricane symbol, you'll see a number. And what I want to show here is that Hurricane Irma was a Category 5 storm, longer than any storm that we've seen on record in the Atlantic. Category 5 storm. What made the storm so strong and for so long? Well, as you saw, lots of ocean heat content that NASA satellites can provide information for, and some NOAA satellites as well. This takes us to our second fundamental question: how will warm ocean waters affect hurricane intensity? And here I need to focus on Hurricane Maria. Maria was a storm that went from a Category 1 to a Category 5 storm in less than 24 hours in September. Less than 24 hours. That's rapid intensification. And those of us in my field know that that remains one of the grand challenges of meteorology, because we've gotten track forecasts to be pretty good over the last several decades. But intensity is a challenge. Why do we get this rapid intensification? And that's been a theme of the hurricane season this year, by the way. GPM, again, can help. We can pop the hood on these storms. What do I mean by that? I like to think of hurricanes as like large heat engines. And when you see hurricanes with traditional satellites, you're often looking at the clouds. But as you're going to see in a moment with Maria, we can now take this satellite data and we can peer inside the hurricane and look at the thunderstorms in the eye wall and rain band. Well, if my wife were sitting here right now, she'd say, so what? That's the way she is. But the reality is there is a huge so what, because when we can see these thunderstorms developing and growing in the eye wall and rain band, they're showing the heat release that powers this engine. And that may very well be a clue that will help us with intensity forecasts. But it's not just satellite data. The global hawk, suborbital platforms, aircraft are also providing unique views, and many of this capability is provided by NASA, our other partners in the industry. And I can't not talk about the performance of our forecast models. Take a look at this model that shows the track of Hurricane Sandy. Studies have shown that if satellite data were removed from the models, we would not have seen that Hurricane Sandy was going to make a left turn into New Jersey and New York 9 days ahead of time. The satellite data is being ingested into the models. Now, this last science question is dear to my heart because it's some of my own research that's sponsored by NASA. There is something called the brown ocean. You might think that storms weaken when they move over land, but we found something different. Take a look at this image. You're seeing soil moisture from SMAP and other things. The red represents dry soil over Texas and Oklahoma. And look what you see, rainfall over several weeks to months. Now watch that change over to blue in Texas. That means the soil is getting wetter, it's moistening up. Here comes Tropical Storm Bill, moves over that wet soil and maintains its strength. It actually even intensified. The brown ocean was feeding the storm just like the ocean would, that wet soil. That's the brown ocean. Now I'd like to introduce Dr. Krista Peters-Ledard. She's a hydrologist at NASA's Goddard Space Flight Center. Krista has developed hydrological models of the water cycle that have been widely adopted by the U.S. Air Force Weather Agency, NOAA, and the U.S. Agency for International Development as critical components for their forecasting systems. Krista currently serves as a deputy director of NASA Goddard's Earth Science Division, where she oversees 5 of the 13 Goddard Earth Science laboratories. She is a fellow of the American Meteorological Society and has been awarded the Arthur S. Fleming Medal given to outstanding federal employees. She's also a friend and a colleague.
Since NASA was created nearly 6 decades ago, this agency and the larger science community has essentially discovered how the Earth works as an interconnected system, as a planet, and we are still discovering. NASA is converting the space-based view of Earth into a pixel-level planetary intelligence system for navigating the challenges of the 21st century. One of those challenges is coping with drought. California, 2015. One of the most productive agricultural markets in the world was racked by a 4th year of drought. Wildfires burned. Crops wilted. Reservoirs plummeted to half of historical averages. But how did this drought spread? How pervasive was it? From space, we track water in the ground, whether it's a centimeter, a meter, or a kilometer below the surface. Let's start with the big picture. Around the world, the GRACE satellites, which is a partnership between NASA and the German Space Agency, have provided unprecedented views of water storage in natural aquifers. These underground reserves are so massive that they affect the Earth's gravity field. And when their mass changes, the satellites detect the change in gravity. Droughts affect deep groundwater stores. In fact, water users can pump hundreds of billions of gallons out of their aquifers to compensate for the lack of rainfall. And GRACE detects this change. This view from space has revolutionized our understanding of water stored beneath the Earth's surface. But scientists at NASA Goddard can provide a more detailed view of conditions in the continental US by combining GRACE data with sophisticated computer models. These computer models help us decompose the GRACE signal into the surface, root zone, and shallow groundwater. And this view can help trigger critical water conservation measures. Stations on the ground provide a connect-the-dots picture, but the vantage point from space, combined with modeling, provides a comprehensive view of the California drought, how it evolved over time and ultimately ended. This constantly changing snapshot of shallow groundwater conditions is now used every week in the US Drought Monitor. This is the benchmark relied upon by decision makers at the local, state, and federal levels. So GRACE gives us a global view, and the combination of satellites and modeling gives us a regional view. But what if I want to know what's happening in a 30 by 30 meter plot of land, the size of a Landsat pixel? California's wine industry provides tens of thousands of jobs, pays $17 billion in wages every year, and is built on intensive agricultural practices. It is also at the forefront of using the view from space to save water and be more efficient. The E&J Gallo Company grows grapes on 100,000 acres across California. Nick Dukuzlian, the company's head of viticulture, said that during the drought, we were farming on a fine line. The model went from commercialization to survival. They use Landsat, which is a joint program of NASA and USGS, to monitor water use and the health of their vines. With constant care and a decades-long record of data, their irrigation strategy was modified, and the vines made it through. Not only that, but water usage was cut in half on some acres. The company uses commercial satellite data too, but as Dukuzlian said, Landsat is the most robust form of imagery across the state. We trust it more. In fact, the company is moving to a system of irrigation that is mapped according to 30 by 30 meter Landsat pixels. Working with IBM and an irrigation company called NetFM, Gallo is developing what they call farming by pixel, taking the foundational data from Landsat and converting it into drip-by-drip irrigation decisions. The company is also talking with its neighbors, the water-intensive almond growers, about the possibilities for their industry. This kind of approach would revolutionize the way people irrigate across the state of California, where, by the way, agriculture brings in receipts of $50 billion per year. So the next time you enjoy a glass of wine or some almonds, you might want to offer a toast to Landsat and to Grace. So California survived its historic drought, and the public and the private sectors are now retooling their long-term plans for managing water. And the view from space will help lead the way. The drought recovery took years, helped in part by massive storms that stretched across the Pacific this winter and spring, and El Niño-driven rain and snow in the years before that. But while the local El Niño impact was beneficial, it also reminded us of why we study the Earth as an interconnected system. When a giant swell of warm water emerged in the Pacific Ocean in 2015, scientists knew to look for impacts. As El Niño changed the global weather patterns, southern Africa went into a severe drought. On top of already dry conditions, the region experienced its lowest rainfall in 35 years. With the SMAP mission, launched in 2015, NASA has dedicated soil moisture measurements for the first time, and SMAP could see this severe drought emerging. SMAP's highly sensitive microwave radiometer detects the energy emitted by the soil depending on how wet or how dry it is. It's like the old gardener's trick. You squeeze a handful of dirt, and you see if it clumps up or if it falls apart. Think of SMAP as doing the same thing with a lot more precision all around the world every 3 days. SMAP allowed us to see the connection between the Pacific Ocean water temperatures and the moisture in the soil in southern Africa. But like with the data in California, these measurements are now being put to operational use more than ever. SMAP's data was fed into the USDA's global crop yield forecast, the Foreign Agriculture Service reports that help drive multi-billion-dollar commodity markets around the world. In fact, the scientists for this region said that with SMAP, they now have the first reliable soil moisture data in 30 years. As the soils dried out, we also used the Terra and the Aqua satellites to assess the impact of vegetation across the countries of southern Africa. These NASA soil moisture and vegetation analyses were also fed into a USAID program called the Famine Early Warning Systems Network. As this drought spread, nearly 30 million people were at risk of drastic food shortages. 4 out of 10 people did not have access to clean drinking water. The global view provided by NASA scientists helped inform USAID decisions about where the agency should send help. In southern Africa in 2015 and 2016, USAID delivered nearly $350 million of emergency water and food aid to millions of people. Our planet's population hit 7 billion people in 2011, and we will likely hit 8 billion in the next decade. We are more dependent than ever on our global food system. At a time when we expect droughts, like the ones you've seen tonight, to happen more frequently, with more severity, for longer periods of time. The challenge is not only feeding 8 billion people, but minimizing conflict. The defense and intelligence communities have named the increased likelihood of conflict due to food and water shortages as one of the key threat multipliers they are watching in the 21st century. Water drives life and the global agriculture system that depends on it. If we want to know and predict what's happening with agriculture locally, we have to understand the system globally. And now, to bring us home, here's Marshall.
Well, there they are. They can't ever say they haven't been on a big screen. Those are my kids. And hopefully tonight you see that this is not about pretty pictures from satellites. These are about narratives of society. It's about their generation and future generations to come. The bottom line is this for me: there is no plan B planet for them or us. Now, Krista and I have shown you several in-depth stories about water, and really only a fraction of the water cycle. Now, keep in mind that NASA is applying the same intensity of monitoring and research to answer key questions about other facets of the Earth system. For example, what are the trends with the world's ice sheets and glaciers, and what does that mean for our coastlines in the future? What do the ongoing changes to the Arctic sea ice mean for the region? Next year, NASA launches the GRACE follow-on and ICESat-2, representing major refreshes of our ice and water monitoring capabilities. And this is important because in order to detect change, we need to see trends, long-term trends. How is life on land and in ocean changing around the globe? How is carbon moving through the air and ocean and land, and what does this mean for our future climate? The coming launches of the Landsat 9 and the JEDI LiDAR to the International Space Station will advance these investigations. How will clouds and aerosols respond to and affect changes in the Earth's system? This remains one of the biggest question marks about our climate system, and there are questions. That's why we as scientists do what we do. These questions aren't just scientific mysteries. Together, they add up to a larger question of habitability on the planet. But there is good news. The good news is that the science has tackled these types of challenges before. Just last month marked the 30th anniversary of the Montreal Protocol, an international agreement struck within years of science identifying a crisis, the ozone hole, which you see here. Now note that the blue represents depleted ozone. That's the ozone hole over the Antarctic region. It would have never been possible without NASA's confirmation from space of the size and persistence of that hole. Now let's walk through a world avoided simulation, just to kind of bring home the value of understanding that that ozone hole was there and doing something about it. On the left is the world with the Montreal Protocol. On the right is what the world's ozone layer would look like in the Northern Hemisphere if we didn't pass the Montreal Protocol. And keep in mind that blue represents depleted ozone. Watch what happens as we approach the year 2017, the year that we're in. Here at the latitude that we are, if we didn't pass the Montreal Protocol, we would have about 10% more ozone depletion, or 10% more increases, if you will, in the damaging UV radiation. Now, UV radiation damages our skin, first of all, it's a health issue, and crops that we depend on for food. So science has risen to the challenge before, and as challenges mount, we'll need it again. But choosing to cast our lot with science is really choosing to put our faith in people. Yes, we face enormous challenges in the years and decades ahead as we push science and society to understand and manage the resources of our home planet. There is no better partnership than the one that we see between NASA, NOAA, USGS, other federal agencies, and the vital collaborations with industry partners, many of which are represented in this room tonight. This partnership will lead the way into the 21st century with optimism that we can solve these challenges together. Our work has just begun. Thank you.